Hello, this is Mr. Mac. This is the first video on the normal distribution. It's being made specifically because I have a lot of students that are out of class for some kind of an FSA test. Now let me tell you, there are two packets that you would need to download from the course web page. One of the packets is this thing that says Lesson 5 Notes, Normal Distribution, and the other one is the Standard Normal Curve Tables. And let me show you what that one looks like just quickly. Okay, Standard Normal Curve Tables. I think I gave you the one where the Standard Normal Curve tables are on one page, and it looks like this. So it should be the next to the last two things on the course web page. The last thing, of course, is the sample test for statistics. You're probably going to want to download that too. There are some rules involved in actually studying on that, though, and perhaps I should mention them now. So let's see if I can find those rules. We want, here we go, this page. Okay, you're going to have your test during session 28 on probability and stat. Now, I have put a sample test online, and it says there are rules about the sample test. Now, these are the rules. You may not ask me any questions about the sample test in class. You may come to me during algebra party or any other time that I have prescription and I'm available to you, and I'll talk to you about them, but you're going to have to pay me something before I'm willing to answer anything. Now, the thing you're going to have to pay me is your work on that question. In other words, you have to show me you've worked at the question before I will answer any questions for you on the test. Now, if you can do those questions, you should have a very, very good idea of how to do most of the questions on the test. If you look at the optional test, you'll see that I have actually taken out a few of the questions. And of course, I'm going to change the numbers on the actual test. But the questions I've taken out of what I refer to as the curveball questions. On those, you're going to have to think a little bit. All right, now let's get started with the normal distribution video 1. Now, the normal distribution is a probability distribution that tells you how likely something will occur that happens in nature. Now, notice the curve here. The curve is actually one of the class of curves that would be f of x is equal to e to the negative x squared. It has a general bell curve shape, and this one is actually called the Gaussian curve or the standard normal curve, and its actual functional statement is f of z is equal to 1 over the square root of 2 pi times e to the negative x squared over 2. I'm sorry, that's negative z squared over 2. Let me just get that whole part there. Negative z squared over 2. Now, it's not all that important for you to know that particular equation just yet, but the idea is this, that Gauss took the general bell curve shape of this function, and he did a couple things to it. This coefficient of the bell curve makes the area under the curve from negative infinity to infinity equal to 1. Now also notice that this curve asymptotes on the x-axis at both ends. So it never actually touches the x-axis, but even when you go out to all the way to infinity, all of the area between the x-axis, or the z-axis, and the curve is equal to 1. Now what we can do then is we can use the area under this curve to be a probability that events will fall into that particular area. Now also, notice there is symmetry with respect to the y-axis. In other words, to the left of the y-axis and to the right of the y-axis, if you were to fold this curve, it would lay down right on itself. Think about this. If the area under the entire curve is 1, and we have symmetry with respect to the y-axis, what would be the area under the curve, just say, to the right of the y-axis? It would have to be 1/2. Those of you watching this video may not have heard that, but one of my Sterling students said 1/2 almost immediately. We won't mention any names, but his initials are John Willits. Anyway, was it the person? Oh yeah, it was John. All right. Now, what do we do next here? Oh yes. Now, many things in life are normally distributed. This curve is very, very useful. We have a list of things down here, and this not an exhaustive list in any way. If you had the SAT scores for high school students, they're normally distributed around some middle. If you did psych exams, I'm not quite sure why that one's in here. None of my students need psych exams, but if you gave a lot of psych exams of some type, you'd find them normally distributed. Now, it says population modeling. Now, what that means is, let's say LG looked at all of their 70-inch flat screen TVs, and let's say they made 2 million of them, and they took the lifespan of the TVs before they failed and weren't able to be used anymore. There would be some middle number of time, I don't know, some number of years, and some of them would not last that long. Some of them would last longer than that. But if they were to plot all of these out, they would find that they would get a curve that looked like a bell shape, or that these curves would be normally distributed. So we can use this curve many times to predict what's going to happen. All right, now, once again, I'm going to write this f of z is equal to 1 over the square root of 2 pi times e to the negative z squared over 2. Now, a couple of things that we talk about here. First of all, the unit 1 from 0 to 1 is on the standard normal curve is 1 standard deviation. So the z scale has units of standard deviation. Now, this is a strange thing. You're going to have to kind of hang on to this for a while as we begin to present this, because a standard deviation is a strange unit. You may or may not have heard of it, but it's a unit that's kind of been made up by statisticians. Now, I'm going to define it for you, but that's not really all that important. It's more like you need to get a sense of what a standard deviation is than to how to compute it. So let's take a look at how you would compute a standard deviation first, so that you can appreciate with me the fact that this unit is really just made up by statisticians, okay? Now let's say you had 10 numbers, A1, A2, up to A10. Now, these numbers aren't in order, like it isn't 1, 2, 3, 4, or 7, 8, 12. They could be just all higgledy-piggledy, but you've got 10 numbers. Okay, and if you wanted to know the standard deviation of these 10 numbers, this is what you would do. First of all, you would find the average. A-V-E-E-R-A-G-E. I can spell. Okay, you'd find the average of the 10 numbers. Okay, and let's call that average, for lack of a better variable or symbol, mu. Okay, notice mean mu. Now, mean is another word for average. So you'd find the average, and then you would, subtract mu from each value. Now, if you take A1 minus mu, A2 minus mu, A3 minus mu, all that kind of stuff, that's what you're doing. What you're finding is the deviations of each data item from the mean. Now, step 3, you would square the deviations. Step 4, you would average the squares of the deviations. And then step 5, you take the square root. And that would be the standard deviation. I don't know about you, but that really seems pretty made up to me. Now, the good news is we have machines now that'll do this for you, but it's an awful lot of work, okay? To find a standard deviation for a data set is an awful lot of work. But what we're more interested in knowing is what it means. Now, hang on just a second here. I'm going to pause, and I'll be back in a minute. Okay, folks, we're back. Now, the question was asked was about the sigma up here in the packet, and that is exactly a good question. Now, this sigma is the small Greek letter sigma, not the capital sigma that you're used to, and add them all up. And you just kind of make a little O with a little curly circle on the top of it to get it. And this is the symbol that we're going to use to stand for the standard deviation. Now, getting back to standard deviation, it's not that important that you know how to compute it, but it is important to know what it tells you. For example, if I said this thing is 1 inch wide, whatever the thing was, you have a sense in your mind of what an inch is. Could you define an inch? Well, probably you'd put up 2 fingers and say, well, it's about this far. You just have a general intuitive sense of how long an inch is, right? If I were to say, we're going to have to walk a mile to get to that 7-Eleven. Again, you could probably define a mile in terms of other unit lengths, but still, the important thing is you have a sense of approximately how far you would have to walk before you would get to the 7-Eleven, so you could have your slushy or Slurpee or icy or whatever it is that 7-Eleven sells. And with the standard deviation, it's the same thing. Now, here's the idea. If we look back at this curve right here, this is 1 standard deviation above the mean. The mean is at 0, and the standard and the z-scores are in units of standard deviation. This score right here is 2 standard deviations above the mean. If your test score were right here, you would be 1 standard deviation below the mean. Now, to help you understand, and this is kind of important, we have what is called an empirical rule, page 2. Okay, now in the empirical rule, notice that with the standard normal curve, 68% of the data falls between -1 and +1 standard deviations of the mean. So when data is normally distributed, you'll find 68% of the data items clustered between plus and -1 standard deviation of the mean. Now, going a little bit farther, 95% of the data items will be clustered between -2 and +2 standard deviations of the mean. And moving a little farther, 99.7% of the data will fall between -3 and +3 standard deviations of the mean. Now, these are the percentages that we expect you to know when we're using the empirical rule. I think the empirical rule is a good teaching tool to help you understand what standard deviations mean. See, let's go back to the 68%. Now remember, the curve is symmetric, so between the mean and one standard deviation, there will be 34% of the data. So now let's say a question. Let's ask a question. Okay, we're going to use a mythical person. Let's call this person Joanna. Joanna scored a z-score of 1 on the Weschler, W-E-S-C-H-L-E-R, test of mathematical appreciation. That's a standard test that measures how much you appreciate mathematics. Okay, now, what percent of students scored lower than Joanna? Now, notice Joanna's score was right here at 1 standard deviation of the mean. Now, these 34% scored below her, and all of these students over here scored below her. And remember, we already know that from here on down is 50%. So Joanna's score was above 84% of the students. It seems obvious, but let's just ask the question, well, what percent of students scored above Joanna on the Weschler test of mathematical appreciation? Well, probability, the number of students that took the test is 100%. 84% scored below her, so 16% would have scored above her. Now, let's go back to the first page, and we want to pick up one more thing, and this is a very, very important thing. It's this equation right here. It says z is equal to x minus mu over sigma. Now I'm going to erase this stuff that tells you how to compute a standard deviation, and we are 18.5 minutes into this video. So I'm going to stop this video and render it, and then I'm going to start the second one. So give me a couple of minutes. Actually, if you're clicking on these things, you could just click on the next video. So we'll be back in a moment. Okay.